Hello everyone, let's begin our new lesson. In this lesson, we will study the linear program model. And in last lesson, we know all our programs start with a model. That is, we should set up a model firstly. We begin with a prototype example. And from this example, we can see how to set up a linear program model. Then we introduce the general steps of setting up a model. Finally, we give some typical examples. That is, we introduce section 1, prototype example, the linear program model, typical examples. Now we see introduction. The development of linear program has been ranked among most important scientific advances. The mid-20th century, its impact since just 1915 has been extraordinary. Today, it is a standard tool that has saved many thousands of millions of dollars for most companies or business of moderate size in various industrialized countries of the world, and its use in other sectors of society has been spread rapidly. Linear program involves the general program of allocating limited resources among competing activities in a best possible way. It can be pressed as the following two cases. Number 1, given some resource, how to use them in best way to achieve the highest profit or reward or performance. Number 2, given a performance task, how to use the fewest resource to finish the task or to achieve the objective. Now we see section 1, prototype example, the Wonder Glass Corporation. The Wonder Glass Corporation produces high-quality glass products, including windows and glass doors. It has 3 plants. Aluminum frames and hardware are made in plant 1. Wood frames are made in plant 2, and plant 3 produces the glass and assembles products. Updated products are being discontinued, releasing production capacity to launch 2 new products having large sales potential. That is, product 1, an 8-foot glass door with aluminum frame. Production 2, a 4 times 6-foot double hung wood frame window. Now the information is listed in this table. The column 1 is plant 1, 2, 3, and this is product 1, 2, and this is the production time of each plant. And the last column is profit per batch. Now in this program, the question is, determine what production rates should be for the 2 products in order to maximize their profits. So we analyze this program. Now in this program, we need to determine the decision variable. X1 means how much product 1 is produced. X2 means how much product 2 produced. So this is the decision variable. In this program, the objective function is maximize profit. Then we describe the profit as maximize Z equals 3x1 plus 5x2. That is, use these row to times decision variables. The constraints are production time. That is, plant 1 production time used is x1 equal less than or equal to 4. Plant 2 used production time is 2x2 less than or equal to available production time is 12. And plant 3, the used production time is 3x1 plus 2x2 less than or equal to 8. So we summarize the model of this problem, that is, maximize z equals 3x1 plus 5x2. Subject 2 means constant, that is, x1 less than or equal to 4, 2x2 less than or equal to 12, 3x1 plus 2x2 less than or equal to 8. And the last is non-negative constant. This is the model of this program. And we note that the objective is linear and all constants is linear too. So we call this is a linear model. Now we see another example. Regional planning. The Southern Confederation kibbutz is a group of 3 kibbutz. The kibbutz is a farmer in Israel. This officer is planning agricultural production for the coming year. And this is some information of 3 kibbutz. Kibbutz 1, 2, 3, 4. 1, 2, 3. Their usable land is 400, 600, and 300. And the water allocation in each kibbutz is in this column. The crops should for this range include sugar beets, cotton, and sorghum. And these are the 3 being considered for the upheat season. The crops differ primarily in their expected net return per acre and their consumption of water. In addition, the Ministry of Agriculture set a maximum quota for the total acreage that can be devoted to each of these crops by the Southern Confederation of Kibbutzim, as shown in the following table. In this table, we note that this is the 3 crops planted in each kibbutz. This is the maximum quota of each crops. This is the water consumptions, and this is the net of each crops. Because of the limited water available for irrigation, the Southern Confederation Kibbutzim is not able to use its eligible land for planting crops in upcoming season. To ensure equity between the 3 kibbutz, it has been agreed that every kibbutz will plant the same proportion of its available eligible land. Now, in this program, the question is, how many acres to devote to each crop at the respective kibbutz while satisfying the given restrictions? The objective is to maximize the total net return to the Southern Confederation kibbutzim as a whole. So we analyze this problem. We first to decide the decision variables. In this problem, the decision variables is some complexity, and we need to decide how acres of sugar planted in kibbutz 1. And we note X11. X11 means how many acres sugar planted in kibbutz 1, and X12 is how many acres sugar planted in kibbutz 2, and X13 is how many acres sugar planted in kibbutz 3, and similar as these decision variables. And in this problem, the objective is to maximize the net return. And we noticed that in this table, the net return of each crops is sugar is 1,000 per acre, $1,000 per acre. Beets is $715 per acre. Sugar is $215 per acre. So we use these numbers to times the planted total acres. That is 1,000 times. This is the sugar beets planted total acres. This is the cotton planted acres, and this is the sugar planted total acres. So this is objective function maximize. And in this problem, the constraints are more complicated. We divided it to a few types. Now we see type 1. Usable lambda for each kibbutz. We know in this table, each kibbutz has a usable lambda is in this column. And in each kibbutz, the use age lambda must less than these numbers. We described as in kibbutz 1, this is kibbutz 1 used lambda, and this is available lambda, so it is less than or equal to. And this is kibbutz 2. Kibbutz 2 used lambda, and this is available used lambda, and kibbutz 3 similar to. This is the first type of constraints. And two type of constraints is water allocation for each kibbutz. And we notice that each kibbutz has water allocation tool. So we describe the water allocation limited. We describe as these constraints. This is the kibbutz 1 use water, and the kibbutz 1 planted 3 crops, and its water consumption is. So we use these numbers to times decision variables. So this is the used water, and this is available water. And similar to in kibbutz 2, kibbutz 3. So this is this kind of constraint. And third kind of constraint is we notice in this table, each crop has maximum culture. Maximum culture is planted total range to limited. We describe these constraints as this. This is crop 1, sugar beets. Sugar beets planted in kibbutz 1, kibbutz 2, and kibbutz 3. And kibbutz 3 planted acres, and we plus it, plus them to all, less than equal to 600. This is number, maximum culture, maximum total. And this is cotton, planted culture limited, and this inequality is sugar, planted land limited. So in this problem, there is another constraint, is equal proportion of each planted in each kibbutz. That is, in kibbutz 1 and kibbutz 2, they have equal proportion land planted. We describe this is kibbutz 1 planted proportion, and this is planted acres in kibbutz 1, and this is the available usable land. So this is kibbutz 1 proportion of land planted, and this is planted 2 portion land planted. So let them equal to. And the true equation is this is kibbutz 2 portion planted. this is keep 3 proportion planted and that ln equal 2. So that is the source constraint. And the last constraint is negativity constraint. That is xj that's greater than or equal to 0. So this is the constraint of these problems. And this model is very large, so we not summarized in a plan. From these 2 examples, we conclude set up a LP model is include 3 parts: decision variable, objective function, and constraints. And we analyze a problem to formulate a model include 3 steps. Step 1, determine decision variables. Think about the problem, what to do. Step 2, determine objective function. Think about generally the problem target. Step 3, determine the constraints. Is generally describe the relationship. Okay, from these examples, we get the general form of LP. The general form of LP is include 3 parts: objective functions, many constraints, and the last negative constraints. The general form is maximize or minimize the subject, the constraints maybe less than or equal to or greater than or equal to. And this is objective function. This is functional constraint or source constraints. And this is negative constraints. Any situation whose mathematical formulation fits this model is a linear program model. That is, the objective is linear and all constraints is linear too. So we call this model is a linear program model. And we describe this model in a table. In this table, this is resource and resources. And the activity. Activity means decision variable. Activity 1, 2, 3, and m. And this is coefficient of sumption, means produce 1, sumption resource 1 is A11. And this is resource 1 available amount. And the last row is object coefficient. That is C1 is produce product 1, maybe get the profit or maybe get the real. Other forms, we now introduce other forms. We now hasten to add the preceding does not actually fit the nature from some linear programs. The other legitimate forms are following. That is, the objective maybe minimize or not maximize. So we describe minimize z equals c1 x1 plus c2 x2 plus n plus cn xn. Some constraints is not less than or equal to, rather than greater than or equal to. We describe it as this equality. Some function constraints is not inequality, it is equation. We describe equal to bi. In the model, maybe xj, decision variable, is not constraint. That is, xj is not greater than or equal to 0. There may be xj less than CL or equal to CL. So this formulation may be in our model. In a linear model, we generally describe J is the value of overall measure of performance, means objective value. Xj describes the level of activity J, that is production. Cj denoted by increase in J that would result from each unit increase in level of activity J, that is coefficient of objective function. Bi is amount of resource I that is available for allocation to activities. Aij is amount of resource I consumed by each unit of activity J. This is the terminology in the model. And the model poses the problem in terms of making decisions about levels of activities. Activities may be produce products, maybe transport products, and so on. So we denote by x1, x2, and xn. This is called decision variables. And Cj, Bi, and Aij is called parameters. It's called parameters. So in these lessons, we have studied the model of linear program. That's okay in these lessons. Thank you very much.